equation. Please welcome Professor LOOS.
Okay, thank you very much. Can you hear me okay?
Yes.
Yes. Okay. All right. So first, let me thank the organizers for giving me the opportunity to present our work today. Yeah, so sorry for the very general title. I was not even sure what to present, so I was thinking, well, let's give a very general title. Is probably not the best thing to do, but well, okay. So for people who don't know me, so our group is working on methodology in electronic structure theory mostly. And we work a lot on excited states, of course, and couplet cluster for excited states. So that's this, and I'm going to talk about it today if I have time. And we work a lot on what we call as well selected CI and as well QMC, post-processing selected CI. And that's what I'm going to talk first. And we work also on other electronic structure theory techniques. So on the complex extension of quantum chemistry methods, it's something that we do like perturbation theory, what we can learn from the complex frame, and also many body perturbation theory. So what I mean by this is like methods like GW or the Bethe-Salpeter equations formalism that can basically replace TD-DFT if you're not happy with your results. So we work also on ensemble DFT, but I think Emmanuel Fromager is going to talk about it on Wednesday, so I'm going to leave that to him. And yeah, so that's it. And so first, let me talk a little bit about selected CI, and that's something I've been working on with my friends and good colleagues, Anthony Semana and Michel Caparel. So that's something that they developed in Toulouse since like several years, almost 10 now. And so what's the idea behind selected CI is that instead of grabbing your singly excited state and after your doubly excited states and your quadruply and triply and quadruply and so on, you're going to use a different strategy that is basically, I'm going to use a criterion, which is usually based on perturbation theory, but you can use something else if you want. And so you're going to grab, like in the entire full CI space, so the full configuration interaction space, the whole Hilbert space, you're going to grab determinants that you think are the most important. Okay? So you're going to do that iteratively until you run out of memory or you think your calculations converge. And so when you're happy with the result or you run out of memory, well, you stop your calculation. And so the idea of this is that basically in the entire Hilbert space, there is actually a very small fraction of determinants that are actually very important for the energy at least, okay? So that's the idea. So the selected CI idea is very, very general, it's very natural. So it's been reborn several times and people have designed methods around this idea. So there is the CIPC methods that has been developed in Toulouse, for example, in the 70s, and that Michel Caparel and Anthony Semana have like rediscovered, let's say. There is the semi-stochastic feedback method from Sairo Somoya and Sandeep Sharma. There is the adaptive sampling CI methods that is roughly the same idea as CIPC, incremental CI, iterative CI, and you can even see like full CI QMC as a stochastic version of selected CI method. So it's something very, very general, okay? So the method that we use in Toulouse at least is CIPC, so CI using a perturbative selection made iteratively. So you're going to use a PT2, so a second order perturbation theory to actually select the determinants in the full CI space. And we're going to do that iteratively, okay? So it's an old idea that has been developed by Jean-Paul Malayev in the 70s in Toulouse and his co-workers, and which was based again on an idea developed by Bender and Davidson even in the late 60s, okay? And yeah, so really CIPC can be seen as a deterministic version of full CI QMC. And you're going to be able to reach the full CI limit within a given accuracy, which is a much smaller number of determinants. So that's the idea, is to target the full CI limit. So SIPC is implementing our homemade quantum package software that is mostly developed by Anthony Semana. Is really like the driving force behind this. And the idea, again, to stress that one more time, is that with SCI plus PT2, okay, so that's the selection of determinants and the PT2 calculation, you're going to be able to reach near full CI quality for total energies and excitation energies for excited state with a very small fraction of determinant of the full CI space, okay? So if you want to know how it works in practice, it's actually very, very black box. There is not much things to do if you want to run a calculation. So I usually give this example because that's a very nice study that has been done by Ericsson and lots of people. And they propose to do a blind test challenge based on benzene molecule in a given geometry, CCPVDZ. And so they give the geometry and the specification of the calculation to several groups in the world, and they say, well, can you give me your best estimate of the full CI energy of that system? So you see that there is many methods. So there is that is something CI from Tubman and co-workers. There is semi-stochastic heat bath theorem from Sarus and Rigar. There is a full CI QMC method from Ali Alavi's group, TMRG, performed by Garnet Chinese group. There's the many-body expansion full CI, and there's this CAD full CI technique as well, which is done by Pierre-Francois group. And so you see that basically that's the best guess, and the result has been found around minus 863 milliards. So that's lots of what you would call basically like state-of-the-art electronic structure methods, and they all agree on more or less on a value of the correlation energy for that system around minus 863 milliards. Okay, so we've done a little follow-up paper on that, or note actually, to show how actually SIPC was performing on this. So as I told you, SIPC is an iterative method. So basically here, that's the variational energy, okay? So it's going to decrease towards the full CI limit that is in black here. So here you're going to increase the number of determinants in your variational space. So your variational space is going to grow so that you select more and more determinants, okay? So basically around here you are like 100 million determinants basically. So it's pretty big in terms of memory. And so you see that in terms of variational energy, the convergence of the energy is pretty slow. But if you add this PT2 correction, second order perturbation field, or a renormalized version that we got a few years ago, you see that you converge much faster towards this limit. So you're not quite there yet, and you're actually pretty far. But what we usually do in practice is that by plotting the correlation energy as a function of the PT2 correction, or its renormalized version, you can actually extrapolate towards the full CI limit. And usually using the largest variational wave function, we do a linear fit so that we obtain the full CI limit, which corresponds to the PT2 correction equal to 0. So there is nothing else to grab. Everything is in the variational space. And it gives like very good estimates of the correlation energy normally. And if we compare to the previous methods that I talked about, okay, and so they're all like still the correlation energy for various methods for benzene, CCPVDZ, same thing. And you see that the SIPC estimate is just there with exactly the same as the CAD full CI value from Piotr. And so that's the type of accuracy that you can get. So here, that's a Hilbert space that is 10 to the power 30, okay, in terms of determinant. So that's not a calculation, a full CI calculation that you're going to be able to do deterministically. You have to use new tricks to be able to do that. The MRG, selected CI, or whatever you want. So that's the kind of thing that we can do with selected CI. So now we've recently improved this thanks to a PhD student who just started his PhD, Yann Damour. And so now we can as well optimize the molecular orbitals at the selected CI level. So why is it important? Is because we're going to converge even faster to the full CI limit. So here, that's the same system. So usually we use the natural orbitals, NOs, so that's the red curve here, and so you converge quite fast, but not as fast as you could. Localized orbital, LOS, gives you, so that's the green curve, is going to give you a slightly faster convergence. So for a given variation on energy, you see that you can compactify the wave function by a factor of 6 or 8, depending on the system. And if you optimize the orbital at the CIPC level, you can even get like the same type of factor. So basically, you can basically compactify a lot, almost by a factor 100 by using orbital optimize. So you can get like much better accurate of the correlation energy. Okay. So it's been extended to solids thanks to the work of the group in Argonne National Lab by Anwar Ben Ali and Paul Kent. And Michel Caffarel has been working a lot like this. And we've done also round separated, combine that with round separation for molecules. It helps again to get very, very accurate estimates of the correlation energy or atomization energy in that case. Okay, and just to show you that quantum package, the nice thing with quantum package is that it's fairly easy to use. It should be like, that's the main purpose of quantum package. And so, for example, it's been used by the group of Professor Kibush. And they use quantum package to design like externally corrected couplet cluster methods, and also like testing their non-expansion combined with selected CI. So quantum package is quite easy to use. So if you are a group that want to use this, you can basically grab it from GitHub and compile it and use it by yourself. It's very easy. And if you have any question, please contact us. All right. So I showed you like some correlation. So it was for ground state energetics here, but we can of course do that for excited states. And we've been doing that for many, many years now with Denis Jacquemin, who's really the driving force behind this project, is to basically use selected CI, where you can actually target excited CI very easily because it's a CI methods, to actually compute very, very accurate estimates of vertical excitation energy in a big bunch of molecules. So that's what we call the Quest database now. And basically the aim of the database is to provide to the community very accurate reference values for excitation energy. So this database is like slowly increasing in size, okay? And now we have up to 600 or 700 like accurate excitation energy, probably like almost usable for machine learning these days. And we have different type of molecules. We have small molecules, organic molecules. We have a set of doubly excited states that are usually quite hard to target with equation of motion methods, for example. We have medium-sized molecules. We have radicals. We have charge transfer excited states. And we try to mix things up to have lots of variety as much as possible, at least. And we have valence or Rydberg excitation, triplets, singlet, doublet, and so on. So if you are interested, my PhD student, Michael Berry, who just like is defending his PhD very, very soon, is designing a website, okay, so that you can go to the website, select the type of molecules that you want, and you can also compare to other methods. So we've done lots of work on the benchmarking side, and so you can compare lots of methods to the reference energies like ADT or CASPT2 and equation of motion couplet cluster and so on. Okay, so if you are interested, go to the website and have a look at this. It might be useful for your research or to do anything else you want. All right, so I still have 15 minutes now, so I can talk about what we've done on the couplet cluster theory for excited states. So that's something that I've been doing with Fabrice, who's a postdoc, Antoine Marie was a student of from the école normale supérieure de Lyon, and again, Michel and Anthony. So very quickly, so the idea behind couplet cluster theory is that you're going to use an exponential ansatz for your wave function. So you're going to take a reference wave function, psi 0, which is very important as a reference. And you're going to apply to it this exponential t factor that is going to create all those terms, t1, t squared, t cubed, and going to give you all those nice properties of couplet cluster methods like size extensivity and so on. Okay. So I'm going to go very on this. Okay, so usually what you have is those T1 and T2 operators, so that are going to generate your singly excited states and doubly excited states, okay? So when you apply T1 to psi 0, you're going to generate all the singly excited states multiplied with T1 amplitudes, that's what we call them. And similarly, if you apply the T2 operator to psi 0, you're going to generate all the doubly excited states, doubly excited determinants, sorry, with the T2 amplitudes, so doubly excited amplitudes, okay? And of course, if you do CI wave function instead, you're going to have this linear ansatz instead of this exponential ansatz, okay? So if you want to the energy at the couplet cluster level, usually you define what we call the similarity transform Hamiltonian. So you take the Schrodinger equation and you multiply on the left by exponential minus t, and this exponential minus t h exponential t is what we call a similarity transform Hamiltonian. Okay, and so based on this, you have two ways of computing the energy. You have what we call the traditional way, which is a projected way where you're going to multiply on the left by psi 0, okay? It's going to give you a very nice expression, and the important point here is that if you do this, you are non-variational, okay? But you can compute this in a polynomial time, okay? So that's nice. You have also the tricky way, the hard way, which is the variational version that is not very used in quantum chemistry, but has some very nice properties that you calculate with the usual variational formula. We can compute the variational couplet cluster energy, but it's usually going to cost you as much as a full CI calculation and even more sometimes. Okay, so that's not very useful in practice, but in theory, it's very useful to learn those kind of things. Okay, so how do you get known of the problems that are the amplitudes? So you're looking for the energy, and to compute the energy, you're going to need, the amplitudes. So the T1 amplitudes and the T2 amplitudes, and you get that by multiplying the similarity transform Schrodinger equations by the singly excited determinants on the left for the first set of residual, and the doubly excited state determinant for the second set of amplitudes. So the double amplitudes and the single amplitudes. You can do that up to whatever you want. Okay. So that gives you a set of polynomial equations, okay, for this and this. And what you're going to do is basically you're going to look for the roots of those polynomial equations, and that's what is going to give you your amplitudes that you're going to plug in the energy expression so that you can compute it. Okay, so it's very easy. Like a couplet cluster calculation, you're looking for roots of polynomial equations. Okay, so let's take a very simple example here. We're going to do pair CCD. So CCD means that you restrict T to just T2, okay? And in the case of pair CCD, you're going to restrict yourself to the doubly excited state that doesn't break electron pairs. Okay, so you take two electrons from one orbital and you put them in another orbital. So you don't unpair the electron if you want. Okay, so it's a restricted CCD calculation if you want. So if you do this, and you can, so I'm going to use a shortcut for those notation. So it's I bar, A bar. So it's a pair alpha beta that goes from I to A. Okay, so I'm going to use only TIA. It's not a T1 amplitude, it's a T2 amplitude, but a paired one. If I write down the per CCD energy expression. So you see that, so that's the zeroth order energy, so the energy of the reference wave function. And here I'm going to have a correlation that only depends on those T1 amplitudes and the 2 electron integrals. Okay, very easy. And to get those amplitudes, what I need to do is I need to solve those residual equations, okay? And RIA is going to be given by a polynomial, that is a polynomial of the T1 amplitude. And you see that it's a polynomial that is quadratic in terms of those amplitudes. There is linear terms in green, if you want. And here you have those orange terms that are quadratic, sorry, in terms of the amplitudes, okay? And because it's a nonlinear set of equations, it's quadratic in the amplitude, you have to use like a Newton type, quasi-Newton usually algorithm to do that iteratively, okay? So you usually use a quasi-Newton, which is basically, so the residual is basically the gradient. So you're going to update the amplitude, the amplitude here, minus the gradient divided by a pseudo Jacobian, if you want, an approximation of your second derivative, if you want, okay? And that's usually how you get at least the ground state energy of your system. And so what has been shown by the group of Schrodinger and Paul Ayers is that if you do a per CCD calculation for ground state per CCD calculation or a DOCI calculation, which is a doubly occupied CI. So it's a CI calculation where you only restrict to the closed shell determinant. Well, you get basically the same energy, okay? And you get it, it's not a strict equality because there is a slight variation in the energy, 10 to the minus 4, 10 to the minus 5, okay? But you get almost the same energy. And so why is it like remarkable? Why? Because basically the per CCD equations can be solved in n cube, okay? And the DOCI is an exponentially scaling method. So that's basically the cost of full CI here, at least in order. And here it's cubic. So basically with a cubic algorithm, you can basically get an energy which is as good as a exponentially scaling methods, okay? So the idea here was to look at that dissimilarity between per CCD and DOCI holds for excited states, okay? So computing excited state at the CI level, like in DOCI, it's actually very simple. You just ask for more rules and you get your excited states. But if I ask you to compute excited states at the couplet cluster level, you're going to tell me, well, how am I supposed to do that? Well, you have one very famous way of doing it and you have one less famous, okay? So the famous one is to use linear response formalism, so equation of motion if you want. So you take your similarity transform Hamiltonian that I showed you before, that you're going to put in the basis of the singly excited states and the doubly excited states, okay? Singly excited determinants and doubly excited determinants. You're going to diagonalize that matrix and it's going to give you excitation energies, okay? So that's the EOM way of doing things. And if you don't want to stop at singles and doubles, you can add triples, quadruples, and so on, and you're going to converge to the full CI limit. So we haven't used that. We went for a different way, which is we're going to use what I call the ground state formalism. It's probably not the best word to use, but that's what I'm going to say today, is that our couplet cluster equations are nonlinear equations, okay? So there is not only one solution, it's like the Hartree-Fock one, you can find other Hartree-Fock solutions. And so what we're going to try to do here is to target higher roots of the couplet cluster equations, okay, and see if they correspond to genuine excited states. So that's not something new. Huh? It's been used before in the 80s and in the 90s by the group of Kowalski. There is a nice review that summarizes things that has been written by Pierre-Francois and Kowalski from 2000. If you want to have a look, that's a very long and exhaustive review where you're going to find all the details. And so that's what we're going to do to try to do today. Okay. So let me give you a small example first. So here I'm taking a helium atom in the 631G basis. So there is two base functions, two orbitals, okay? So I'm going to write HOMO L and LUMO L, okay? And for example, we're going to look at the residual equations. So remember that the solution corresponds to the roots of that polynomial. Here I've got only one amplitude that corresponds to the HOMO to LUMO transition. And if I plot the residual equation in terms of T, well, I get two roots. One root that corresponds to the ground state and one root that corresponds to the doubly excited state. So I forgot to tell you, but per CCD, we're only going to target doubly excited state because you only consider paired doubly excited determinants. Okay? And so if you look at the integrals of that residual, okay, so you can see that the ground state corresponds to a nice minimum, but here the doubly excited states in the helium atom correspond to a maximum. Okay, so if you have the right algorithm, you should be able to converge to that doubly excited state. Okay, so if you use the usual algorithm, you're never going to be able to converge to that maximum because you're going to be pushed down to the ground state solution, and that's usually what you want in your code, so that's okay. And so to be able to converge to that maximum solution, okay, we're going to have to use information about the curvature of the surface. And so we have to compute the exact Jacobian that is associated with the per-CCD equation. So it's not very hard. You can compute this. And by using a genuine Newton-Raphson algorithm where you take into account the second derivative of your energy with respect to the amplitude, you're going to be able to converge to that excited state, and that corresponds to a genuine excited state, okay, that you can compare. And if you do that for systems, so let's say we take H4 and small basis STO6G, and we compare per CCD and DOCI with R3 for ground state orbitals, you see that you recover the result from Scuderia and Polaios group, so the dots are the DOCI numbers, okay, for ground state, first doubly excited state, second doubly excited state, doubly, and so that guy here is the quadruply excited state, okay. Sorry, and so you get basically the same energy for the ground state, but you see when you go higher for the higher excited states, you get absolutely rubbish, okay? And you see that you even get, so the black dash line basically are complex solutions, okay? So basically it works for the ground state, but if you use at least the R3 for ground state orbitals, it's not going to use for the excited state. Well, you're going to say to yourself, well, that's a bummer, but you can do better than this. And what you can do is to optimize the orbitals at the per CCD level. So here I'm running out of time, so I'm going to go very quickly, but that's the usual algorithm to optimize orbital that you would use in classes here for an orbital optimized couplet cluster. So you're going to optimize the amplitude, and at the same time, you're going to optimize the coefficient of your orbital, of your molecular orbital. And so you can do that iteratively. Okay? So you just do your per CCD calculation, compute your density matrices, compute your orbital Asian on the right hand, and make like this. If you do this, you perfectly match the DOCI or DOCI. So basically what I'm trying to tell you here is that if you optimize your orbitals at state-specific levels, so specifically for given excited states, you can get with per CCD basically the same energy as DOCI. And it works as well for large molecules. So here it's a doubly excited state of CH+, and you can see that basically, we've done that for other molecules, BH and so on. And basically, by doing this state-specific orbital optimized per CCD calculation, you can get quality which are basically on par with CCSDT, okay, UM-CCSDT, even better sometimes. And it's all in quantum package. If you want to try it, you can clone the repo and compile it, and Fabrice repository is here, and so it's very easy to use. So if you have any question, please let